Hello learners, I am Dr. S.S. Gomathi, Associate Professor from PG and Research Department of Physics, Sri Sharda College for Women, Autonomous, Salem. Let us learn about numerical integration in this lecture. Outline of my presentation: Introduction, Newton-Cotes quadrature formula, types of numerical integration, Trapezoidal rule, Simpson's rule, Weddle's rule, and again Simpson's rule is classified into two types: Simpson's 1/3 rule and Simpson's 3/8 rule. Truncation errors, example problems, summary, multiple choice questions, references. Let us see an introduction about numerical integration. In graphics, many quantities we are interested in are naturally expressed as integrals. For example, total brightness, total area. For very simple integrals like integral 0 to 1 by 3 x squared dx, we can compute the solution analytically. Here, if we integrate 1 by 3 x squared dx, that is x cubed, and when you apply the limits between 0 and 1, we will get the answer as 1. For everything else, we have to compute a numerical approximation. So basic idea about numerical integration is integral is area under a curve. Sample the function at many points. Integral is approximated as weight sum. We know that integral a to b f of x dx represents the area between y is equal to f of x, the x-axis, and the ordinates x is equal to a and x is equal to b. This integration is possible only if f of x is explicitly given and if it is integrable. The problem of numerical integration can be stated as follows. That is, for a given set of n plus 1 paired values xi, yi, where I takes the value 0, 1, 2, etc. up to n of the function y is equal to f of x, where f of x is not known explicitly, it is required to compute integral x0 to xn y dx. So in the graph shows that the area under the curve y is equal to f of x can be written as integral a to b f of x dx. So integral is nothing but area under the curve. As we did in the case of interpolation or numerical differentiation, we replace f of x by interpolating polynomial Pn of x and obtain integral x0 to xn Pn of x dx, which is approximately taken as the value for integral x0 to xn f of x dx. So let us start with the derivation of Newton-Cotes quadrature formula. For equally spaced intervals, we have Newton's forward difference formula. That is, we are going to derive Newton-Cotes quadrature formula from Newton's forward difference formula. Y of x is equal to y of x0 plus uh. When you expand this, you will be getting y0 plus u into del y0 plus u into u minus 1 by 2 factorial into del squared y0 plus etc. And we'll name this as equation number 1. Now, instead of f of x, we will replace this by interpolating formula of Newton. That is, u is equal to x minus x0 by h, where h is nothing but the interval of differencing. Since xn is equal to x naught plus nh and u is equal to x minus x naught by h, we have x minus x naught by h is equal to n is equal to u. This, if you rearrange the terms, you'll be getting this equation. And therefore, I can write now integral x naught to xn f of x dx is equal to integral x naught to xn plus x naught plus nh. That is, you are replacing xn by x naught plus nh. So when you replace that, again we are going to replace this f of x by the interpolating polynomial Pn of x. So now the integral becomes integral x naught to x naught plus nh Pn of x, and this is of degree n. Now you substitute equation 1 in this integral, and even this x naught plus nh can be replaced as integral 0 to n. That is explained here. That is, we are going to change the integral which is in terms of x into integral in terms of u. Therefore, we are going to replace x in terms of u, where dx will take the value h du, and when x is equal to x naught, u will become 0. And when x is equal to x naught plus nh, u will become n. And therefore, this integral can be rewritten as h integral 0 to n. Now we are going to replace everything in terms of u. So y naught plus u del y naught plus u squared minus u by 2 factorial to del squared y naught plus etc., which in terms of, we are going to integration in terms of du. Now, after integration, you will be getting this expression where you are going to apply the limits between 0 and n. So after applying the upper limit, you will be getting the equation like this one, which can be named as equation number 2. And this equation 2 is called Newton's quadrature formula, and this will be a general quadrature formula. By substituting the various values of n here, you can get a number of special formula, which we'll be discussing in further slides. We'll start with trapezoidal rule. In this, we are going to consider the Newton-Cotes quadrature formula in terms of n. This is the formula which we derived earlier. Now, putting n is equal to 1 in this Newton-Cotes quadrature formula, we have, so when you substitute n, this will become n is equal to 1. So h is common outside. 1 into y naught plus half into del y naught, and leaving the other terms since they do not exist when n is equal to 1. Now, this del y naught, we can write it as y1 minus y naught. Therefore, the first term is y naught plus half into, instead of del y naught, we are replacing that by y1 minus y naught. So when you simplify these three terms, you will be getting h by 2 y naught plus y1. We'll name it as equation number 3. Now, integral x naught to xn, that is equal to integral x naught to x naught plus nh f of x dx. You can split this integral by applying the limits. That is, the first integral is x naught to x naught plus h, and you have to start the second integral from x naught plus h into x naught plus 2h. Similarly, you can repeat this up to n times. Therefore, the last integral will be integral x naught plus n minus 1 into h up to x naught plus nh f of x dx. So finally, when you add all these terms, you will be getting integral x naught to x naught plus nh, which will be the original integral. So now, since we got the expression number 3, that can be applied to the other other integrals also by applying the same procedure. So for the first integral, the answer will be h by 2 y naught plus y1. For the second integral will be h by 2 y1 plus y2. Similarly, up to h by 2 yn minus 1 plus yn. So when you add all these terms, you will be getting a simplified expression like this, which is h by 2 y naught plus yn plus twice y1 plus y2 plus y3 up to yn minus 1. So this I can write in words, that is h by 2 sum of first ordinate. Y naught is taken as the first ordinate and yn is the last ordinate. So I can replace these two terms as sum of the first and the last ordinates plus twice sum of the remaining ordinates. The interpolating polynomial is linear and there are only paired values, and this rule is called trapezoidal rule. Geometrical interpretation of trapezoidal rule. If the ordered pairs xi, yi, I is equal to 0, 1, 2 up to n are plotted, and if any two consecutive points are joined by straight lines, we get the figure as shown. The area between f of x, that is this curve, the x-axis, and the ordinates x is equal to x0 and x is equal to xn is approximated to the sum of the trapeziums, and hence the name trapezoidal rule. So in this graph, we can see that when you cover the area between the curve y is equal to f of x, and this is the curve y is equal to f of x, and this is your x-axis, and the ordinates x is equal to x0 and x equal to xn. So now you can see there are so many trapeziums here. So therefore the name trapezoidal rule comes from the name sum of the trapeziums. Though this method is very simple for calculation purposes, the error is significant. The accuracy of the result we can improve by increasing the number of intervals or decreasing the value of h. Simpson's 1/3 rule. We'll see the derivation of this formula. Again, we are going to start with Newton-Cotes quadrature formula, and this is your Newton-Cotes quadrature formula. Here we are going to put n is equal to 2, and therefore you will be getting an expression like this. So when you replace n as 2 and other terms here also, it gets vanished, and after that you will be getting an expression like this. And this del squared y0 is del y0 is as usual we will replace by y1 minus y0, and here this del squared y0 you are going to replace that by e minus 1 the whole square into y0. So after simplification, you expand all this, collect the similar terms. When you simplify that, you will be getting an expression like this, and still it can be further simplified as h into 1 by 3 y2 plus 4 by 3 y1 plus 1 by 3 y0. This h by the 1 by 3 can be taken outside, so it is h by 3 into y2 plus 4 y1 plus y0. Again, this we started with n is equal to 2. So here we have changed as the integral limits as x0 to x2. The same can be applied if we change the integral limits between x2 and x4. And therefore, you will be getting h by 3 y2 plus 4 y3 plus 5 y4 correspondingly. So this again I am doing for I times. The xi to xi plus 2 f of x dx will now become h by 3 yi plus 4 yi plus 1 plus 4 yi plus 2, that is h by 3 into yi plus 4 yi plus 1 plus 4 yi plus 2, and here you will be getting the generalized formula. If n is an even integer, last integral will be this one, that is xn minus 2 to xn. This will be the last integral. You can divide the integral into many integrals, and adding all these integrals you will be getting this final value. This I am going to do in this equation. So let us see what will be the answer for the last integral, that is integral xn minus 2 to xn f of x dx. You will be getting this value. When you add all these integrals, you started with x0 to x2, x2 to x4, something like that. So the number of ordinates y0, y1, yn is odd. We have integral x0 to xn is our original integral value, and this we divided into number of integrals like x0 to x2, x2 to x4, etc. up to xn minus 2 to xn. And we are going to substitute the integral value for each and every integral, and therefore this will be the consecutive substitution. And after that, you will be combining all the similar terms, and you will be left over with this equation, which is h by 3 y0 plus yn plus twice y2 plus y4 plus etc. plus 4 times y1 plus y3 plus etc. Here I am going to summarize this as h by 3 into, this will lead to sum of the first and last ordinates, and this sum of remaining odd ordinates and then plus 4 times sum of even ordinates. And next is Simpson's 3/8 rule. Here also we are going to use the same Newton's quadrature formula. Putting n is equal to 3 in Newton's quadrature formula, we have this type of equation. The similar method which we applied for trapezoidal rule and Simpson's 1/3 rule can also be applied here. And we have to replace del y0 by y1 minus y0 and del squared y0 by e minus 1 the whole squared into y0 plus del cube y0 by e minus 1 the whole cube into y0. Again, you have to expand all this, simplify this, you will be getting an expression like this. Finally, coming to the last thing where the regular procedure is, we will be splitting the main integral into number of individual integrals, and after adding all these, you will be getting the final formula for Simpson's 3/8 rule. So as usual, here it is x0 to x0 plus 3h. We are going in terms of multiple of 3. And x0 plus 3h to x0 plus 6h, etc. Whereas the last term will be x0 plus n minus 3h up to x0 plus nh f of x dx. So when you substitute for each and every integral as usual, and then we have to keep on combining the similar terms. After simplification, you will be getting an expression 3h by 8 into y0 plus yn plus 3 times y1 plus y2 plus y4 plus y5 plus etc. up to yn minus 1 plus 2 times y3 plus y6 plus y9 up to yn minus 3. We'll take this as equation number 2, which is Simpson's 3/8 rule, and which is applied only when n is multiple of 3. And the last rule is Weddle's rule. We have seen already trapezoidal rule, Simpson's 1/3 rule, Simpson's 3/8 rule, and the third one is Weddle's rule. So again, taking into consideration Newton's quadrature formula, here we are going to substitute n is equal to 6. In trapezoidal rule, we substituted n is equal to 1. In Simpson's 1/3 rule, it is n is equal to 2. In Simpson's 3/8 rule, we took n is equal to 3. Whereas in Weddle's rule, we are going to take n as 6. So again, here the limit here now will become x0 to x0 plus 6h. N will take the value 6 here. So after that, as usual procedure, we will be replacing the corresponding terms. So here it is given as replace the term 41 by 140 del power 6 y0 by this quantity. And then by this change, the error introduced is only h by 140 del power 6 y0, which is negligible, and h and del power 6 y0 are small. As usual, del is replaced by e minus 1. And replacing all differences in terms of y's, we get integral x0 to x0 plus 6h f of x dx will be 3h by 10 y0 plus 5y1 plus y2 plus 6y3 plus y4 plus 5y5 plus y6. Similarly, for the second integral, we will be starting the lower limit as x0 plus 6h and the upper limit will be x0 plus 12h. The answer will be correspondingly like this. So this can be extended to the last integral, where the lower limit will be x0 plus n minus 6h, the upper limit will be x0 plus nh. So again, the equation you will arrive at the answer like this. Now, combining all these integrals or adding all these integrals, you will be getting from x0 to xn plus x, that is integral x0 to x0 plus nh, f of x dx will take the value like this. We will name it as equation number 1. And this equation 1 is called Weddle's rule. So now we can have a short grouping of this coefficients to remember in an easier way. First group coefficients 1, 5, 1, 6, 1, 5. That is, here it is. These are called the first group coefficients. 1, 5. The coefficient of y0 is 1. The coefficient of y1 is 5. Therefore, 1, 5. For the third and fourth term, it is coefficient is 1. Here it is 6. So 1, 6. Here it is again 1, 5. So we are considering only the coefficients here. All interior groups coefficients will be, see here, 2, 5, 1, 6, 1, 5. Even for the next term, it will be like this only for all interior groups. So we are considering into three categories. One is the first group, all the interior groups, and finally the last group. For the last group, it is 2, 5, 1, 6, and 1, 5, and finally the fourth term is left over as 1. So from this, I can come to the conclusion that if there are only 7 ordinates, the coefficients are 1, 5, 1, 6, 1, 5, and 1. So in order to easily remember the coefficients, we are grouping the coefficients into first group coefficient, interior group coefficients, and then last group coefficients. So 7 ordinates are necessary for this Weddell's rule. So truncation errors, when we perform these type of integration, that is using definite integration with the help of a trapezoidal rule or Simpson's rule, we land up with the truncation errors. We'll see what is truncation error. These errors result from using an approximation instead of an exact mathematical procedure. So two kinds of truncation errors in numerical integration are possible. One is local truncation error, which is caused by one iteration. And second one is global truncation errors, which is due to the cumulative error caused by many iterations. So in trapezoidal rule, modulus E less than or equal to B minus A h power 4 divided by 180 into m. Here m stands for the maximum value of this y dash, y double dash, etc. And in trapezoidal rule, the order of that is the truncation error is of the order of h square. That is, whereas in Simpson's 1/3 rule, the truncation error is of the order of h power 4. Whereas the truncation error in trapezoidal rule is of the order of h square. In Simpson's 1/3 rule, the truncation error is of the order of h power 4. So we'll discuss some example problems using the above rules. Evaluate integral -3 to +3 x power 4 dx using trapezoidal rule and Simpson's rule. Verify the results with actual integration. So whenever you are asked to find out Simpson's rule, you are supposed to do both Simpson's 1/3 rule and Simpson's 3/8 rule. And after performing the integration by using these rules, you are asked to verify the result with actual integration. So we can compare the level of accuracy with numerical method of integration and with ordinary integration. Let us see how to perform the integration. So coming to the solution, y equal to x power 4 is the given interpolating polynomial. The interval length is b minus a, where b is the upper limit and a is the lower limit. So 3 minus of minus 3 will give you 6. So now I'm going to take h equal to 6 by 6, that is equal to 1 with 6 equal intervals. So now that is b minus a by number of intervals. So 6 by 6 is 1. We are going to form the below table. So now consider the x value. You start with the lower limit minus 3. With the interval of 1, you can have minus 2, minus 1, 0, 1, 2, 3. You are going to form the table with the help of the h value. Since you have fixed the interval as 1, that is interval length as that is equal to, that is the difference between these two as 1. I can start with the lower limit. Keeping the difference 1, I can go up to the extreme, that is upper limit. And with this, I can form the value for y. Here the function is x power 4. So when you substitute x to be minus 3, so minus 3 the whole power 4 will give you 81. Minus 2 the whole power, for each and every x value, you have to find the corresponding y value. So minus 2 the whole power 4 will give you 16. Minus 1 the whole power 4 will give you 1. 0, any of 0. 1 power 4, 1. 2 power 4, 16. And 3 power 4 is 81. So with the help of this table, we are going to start with trapezoidal rule. And before that, we'll name the ordinate. This is the first ordinate, second ordinate, third ordinate, 4, 5, 6 and 7. So 7 ordinates are there. Let us name the first ordinate of y as y0. second ordinate of y as y1, similarly up to y6. So don't get confused with the ordinate and with the y value. That is, it is different because this is the first ordinate, but you will be getting this is y0. The second ordinate is said to be the even ordinate, but when you name that, it will be y1. The suffix is 1, it is odd. So don't get confused with these two because this is said to be even ordinate, but y1 is the name we are using for the even ordinate. That is used to represent the even ordinate. So we'll start with the trapezoidal rule, and the formula for finding the trapezoidal rule is given here, and h is taken as 1. So when you substitute the corresponding values from the table, and these are said to be the remaining ordinates. So when you take the first ordinate as 81, the last ordinate is 81. This is sum of the first and the last ordinate. So 81 plus 81 and plus 2 times remaining ordinates. You have to add all the remaining leftover ordinates. You will get the answer as 115. Let us see what we are getting in Simpson's 1/3 rule and 3/8 rule. So by Simpson's 1/3 rule, the formula is like this. And when you substitute the values, this is said to be the odd ordinate. So it's for easy remembrance. I've written here as y2 and y4. So you can take down the corresponding values. When you substitute and simplify this, you'll be getting the answer for the integral as 98. By Simpson's 3/8 rule, similarly, you'll be getting the answer as 99. And the last step is we are going to compare all these three with the actual integration, where it is the normal integration. When you integrate x power 4, it will be x power 5 by 5. Upper limit minus lower limit will be getting 97.2. So when you compare all these results, that is 115, 98, 99 and 97.2, we can come to the conclusion that Simpson's rule gives better result than trapezoidal rule, because the 98 and 99, they are almost equal to 97.2, but whereas 115, which we obtained from trapezoidal rule, is getting deviated more from the original integration. The error is more in this case, and already we have discussed that the error is significant in trapezoidal rule, and therefore we are giving importance to Simpson's 1/3 rule and Simpson's 3/8 rule. So the conclusion from this problem is Simpson's rule gives better result than trapezoidal rule. We'll see another example problem for Weddle's rule. Here, evaluate integral 0 to 6 1 by 1 plus x dx using Weddle's rule. Solution: number of intervals here is taken as 6, and therefore h is equal to 1 again. You can form that is x is equal to 0, 1, 2, 3 up to upper limit. Again you have got 7 ordinates here, and y is equal to 1 by 1 plus x, and therefore you can form this table. And from this will be actually 1 by 2, 1 by 2, 1 by 3, 1 by 4. When you substitute the various values of x here, for example, when you substitute the first value of 0 here, 1 by 1 plus 0 will give you 1. For the second value, it is 1 by 1 plus 1. You have to replace this x by the corresponding x value. Similarly, when you go on for the for all the values, you can form the table like this. Again, you can name the ordinates as the first ordinate as y0, second ordinate as y1, third ordinate as y2, and the fourth ordinate as y3, etc. up to y6. So up to y6, this is seventh ordinate. You should be very clear in understanding the ordinates. Here you have got 7 ordinates, but when you represent the ordinates by the value y, it is y0, y1 up to y6. So we have already derived this Weddle's rule, and the formula is like this. So you can replace the corresponding values here, and therefore when you replace the values here, you will be getting the answer as 1.95285714. So this is how we can apply Weddle's rule to find out the actual that is integral value for the given problem. So let us have a quick summary about what we have discussed in this lecture. Numerical method is a set of mathematical techniques used to solve problems. Numerical integration is calculating numerical value of a definite integral. One interpretation of a definite integral is area under a curve. We have seen that. Newton quadrature formula is a general quadrature formula for various special formula. A numerical integration are used to estimate the values of definite integrals when a closed form of the integral is difficult to find, or when an approximate value only of the definite integral is needed. The most commonly used techniques for numerical integration are the trapezoidal rule, Simpson's rule. In that, Simpson's 1/3 rule and 3/8 rule, and Weddle's rule. And this we have discussed all the 4 type of integration. In trapezoidal rule, y of x is a linear function of x. The rule is the simplest one, but it is least accurate. Whereas in Simpson's 1/3 rule, y of x is a polynomial of degree 2. To apply this rule, n, that is, the number of intervals must be even and the number of ordinates must be odd. This is the condition for applying Simpson's 1/3 rule. So once the problem is given here, you can check whether the number of intervals you are getting as even number or the number of ordinates as odd. If these two conditions are not satisfied, you can very well come to the conclusion that Simpson's 1/3 rule cannot be applied to that type of particular problem. Similarly, Simpson's 3/8 rule, y of x is a polynomial of degree 3 here. To apply this rule, the number of intervals is a multiple of 3. Since we substituted n is equal to 3 here, n is equal to 2 and n is equal to 1. Even with that value, you can very well keep in mind that Simpson's 1/3 rule is a polynomial of degree 2, whereas Simpson's 3/8 rule, it is a polynomial of degree 3. In Weddle's rule, y of x is a polynomial of degree 6. To apply this rule, n, the number of interval is multiple of 6 and minimum number of 7 ordinates is necessary. So these are the conditions to be checked to apply this particular rule for a particular problem. When any of these conditions is not satisfied, we can very well state that this rule cannot be applied to solve this particular integral. Hope you have enjoyed learning, and shall we have a quick assessment about our understanding by going through this multiple choice questions one by one. Let us start with the first question and try to answer them. The error in the trapezoidal rule is of the order of h square. The error in the Simpson's rule is of the order of h power 4. Hope you can recollect the content. Simpson's 1/3 rule of integration is exact for all polynomials of degree not exceeding 2. Simpson's 3/8 rule is applicable only when n is a multiple of 3. In Simpson's 1/3 rule, the number of interval must be even. The 2-segment trapezoidal rule of integration is exact for integrating first order polynomials. The process of numerical integration of a function is a single variable is called quadrature. Some more multiple choice questions. While evaluating the definite integral by trapezoidal rule, the accuracy can be increased by taking large number of subintervals. A minimum number of dash ordinates is necessary for Weddle's rule. This we have discussed as 7. The least accurate method is trapezoidal rule. In deriving the trapezoidal formula for the curve y equal to f of x, each subinterval is replaced by its chord. The degree of y of x in trapezoidal rule is 1. The degree of y of x in Simpson's 1/3 rule is 2. The degree of y of x in Simpson's 3/8 rule is 3. Hope you are able to answer all the questions. And these are the references, numerical methods by P. Kandasamy, K. Gunavathi, K. Tilagavathi. These are the books I referred for preparing this slides. Numerical methods in science and engineering, Venkatraman, MK. Numerical methods by A. Singaravelu. And some of the ideas I've taken from NPTEL lecture contents and some Wikipedia references also I've taken. As per the saying of Albert Einstein, logic will get you from A to B, imagination will take you everywhere. Thank you.